outline, but I'm just going directly by the outline. If I don't say something that's on the outline, it's not on your comp. Okay, some of it, a lot of it is redundant.
Is the outline on canvas?
Huh?
Is the outline on canvas?
Yeah. I believe I put it in your lab class. Does anybody remember?
I think you did.
Yeah, I'm pretty sure. So look in your lab class for the outline. Keep in mind, you guys, that outline is directly from the ARRT. So that's what the ARRT is saying. That might be on your exam. So if you look at it and you see, like the first section, it says safety and in parentheses 53. That just means that there may be 53 questions on safety. So anywhere you see a number, that's the number of questions that might be on your exam. Okay, so starting out with X-ray production, 4 things needed. Okay, what's the first thing that's needed to produce an X-ray? Good, electrons. So we need electrons. No, you guys don't, I'm talking about in the target, in the tube itself. I'm not talking about these, which I'll get to in a minute. We're talking here about everything that happens inside the X-ray tube, okay? All right, so are there electrons once it comes out of the tube? What are they? All right, okay, so no electrons ever come out of the tube. Don't let the registry trick you. Sometimes they'll say, how many cathode ray electrons are produced and how much heat? There's no cathode ray electrons produced. Okay. All right, so we need a source of free electrons. How do we get that? Good, thermionic emission. What does that mean?
It's when the electrons are boiled off.
Boiled off of what?
Okay.
From the filament. Okay, so you have to boil off some electrons from the filament. How many filaments do we usually have?
2.
2. Okay, so we usually have 2 filaments. So the electrons are boiled off, and something, I don't like how the outline goes, but something keeps them in a cloud. What keeps them together? The electrons. What? Focusing cup. Okay, so we need to keep them together for a little bit. So the focusing cup keeps them together. What's the focusing cup made out of? Good, molybdenum or molybdenum or however you want to say it. Sometimes nickel. Okay, what's the focusing cup given? What kind of charge?
Negative.
Good, the focusing cup is given a negative charge, and that's what keeps those electrons in a little cloud. Okay, then we need acceleration. We need the electrons to travel from cathode to anode. What does that? High voltage circuit. So we need them to accelerate. So the high voltage circuit pulls the electrons across the tube, and then we need deceleration of the electrons when they hit the target. Okay, thermionic emission, keep them in a focusing cup, acceleration and deceleration. What's the anode made out of?
Tungsten.
Good, tungsten. So is the cathode, right? So is the filament. It's made out of tungsten. Right. Why do we use tungsten?
It has a high boiling point.
Good, high boiling point,
And it's very strong.
high atomic number. And in the case of the cathode, you can make it into a thin little wire, which is what the filament is. Okay. Okay, so those electrons slam into the target. 2 things can happen when the electrons slam into the target. The first one, I think, is the easier one. It's called brems. You need to know the other names for brems. Okay, brems, or bremstrahlung, actually. General light breaking, because that's where they slam, breaking. Heterogeneous and polyenergetic. When do we get brems interactions? Yeah?
Yeah.
What else? You get brems at any kVp you set. Usually the tubes go up to 150. So from 1 to 150 kVp, you can get a brems. Okay. You might see KeV. KeV just means electron volts. Just means the energy, kind of the same thing. kVp is just the peak, the highest. All right. So what happens with brems? How do we get that photon energy? No. So the electron comes over and it interacts with the nucleus of tungsten. And it's slowed down. It's deviated. Basically, all you need to know is that slowing down is what creates the photon. The deceleration is what creates the photon. Okay, so 1 to max kVp, you can get a brems occurring, brems interaction. The other one is called characteristic, and you need to know the other names for characteristic. It's also known as homogeneous, monoenergetic. Not very many energy levels that occur in characteristic. So how does characteristic happen? All right, so the electron comes over and it interacts with the K shell of tungsten. What's the atomic number of tungsten? 74. So the atomic number is 74, so the shells coming from the nucleus out, it just gets less and less energy, binding energy. Okay. So anyway, so the electron comes over and it knocks this K shell out, K shell electron out. Then one of these other shells, or maybe a free electron, will go in and fill the gap. Okay, so if we start with 69.5 K shell, and let's say the L shell fills in. That's 57.4 keV. That's how much energy that photon has. Okay? So let's say the M shell fills in. You get an electron from the M shell. We get an X-ray photon of 67.4 keV. Let's say a free electron fills it in. Then we get a photon of 69.5. So that's why they say it's monoenergetic. There's not very many ways this happens. There's not very many X-ray photons created by characteristic. So at 100 kVp, how much is characteristic? What percent? Did y'all forget all this stuff?
10.
10 to 20. At 100 kVp, there's only 10 to 20% characteristic. At 100 kVp, there's 80 to 90% brems. Can we get characteristic at less than 70 kVp that you set? No. That electron has to have enough energy to knock out this K shell. So if an electron comes over and knocks out the L shell, what are you going to do with the 12 kVp photon? Nothing. Okay. So it has to have at least 70 to create a brems. Okay, so let's say you have a brems photon and a characteristic, and you set 100 kVp. Could you tell the difference? They all look the same, it doesn't matter. Okay, one was just created by Brems and one was created by characteristic. Do you guys understand this? Sort of.
Sort of, I'm sure we'll get better.
If you don't, now's the time to ask.
Do you have to do a math problem like that? Just curious. Oh, okay.
No, I won't ask you to do, I just wanted to show you the numbers, so you understood it. I don't think this would, who knows, but you need to know at least 70 kVp is needed to produce characteristic.
So REMs are created from 1 to 150 kVp.
Brems can occur at any energy, or any kVp you set.
And characteristics happen at lower kVp.
No, it have to be above 70 kVp. That electron has to have enough energy to knock out the cation, which is counted at 69.5.
But at 100 kVp, only 10 to 20% characteristic is in.
Yeah.
Okay.
Very discrete, that's why some books call it discrete. All right. The next thing on your list, on your outline is X-ray beam number 3, frequency and wavelength. What's the frequency? No.
How much energy is that?
How fast the waves move?
Cycles per second.
Yeah.
Okay, frequency is cycles per second. What's wavelength?
How long the waves are?
Or the distance, the wavelength is the distance from one sine wave to another, whether it's from peak to peak or valley to valley. Okay, so it's the distance from one sine wave to the other. How are frequency and wavelength that's what I'm looking for. How are they related? Frequency and wavelength are related how? Inversely, good. Frequency and wavelength are inversely related. If you have a high frequency photon, it's a short wavelength, inversely. High frequency, short wavelength. Low frequency, high wavelength. Okay. What about energy? How is energy related to frequency? Directly related. High frequency is high energy. All right, electromagnetic spectrum. So you might want to write this down because with the other two labs, I know you guys didn't get the definition in class. So electromagnetic spectrum, the definition is it's an electric and magnetic disturbance traveling through space at the speed of what? Good, light. Perpendicular to each other. Okay, so everything in that spectrum, they're called photons, and they all travel at the speed of light. Okay, so if I said to you, knowing what I know you know, which one has a higher frequency, radio waves or X-rays? All right, okay, so I'm gonna start with the lowest frequency, and you guys might see in books, they have other parts of the spectrum in there, like radar, but the one from, I guess you guys use Bouchon, it doesn't have it. Cosmic rays are also part of the spectrum, but it's not in the book. Okay, so starting at the lowest frequency, which is what kind of wavelength? Long or short? Long wavelength. Okay, lowest frequency, longest wavelength, radio waves. Good, I heard someone say it. Next one coming up the spectrum is, guys remember? Good, microwaves. What's next? Infrared. Okay, next one is visible light. Make a little star by visible light and write down, I see it on a lot of registry stuff, that is the narrowest portion of the spectrum is visible light. Okay, next one is ultraviolet. Then X-rays. And last, according to that book, is gamma. No, you don't have to know the numbers that correspond to them. Like
There's
10
more
to-
after. Is there more after gamma or?
Do what?
There's more after gamma?
Some books say cosmic are the highest energy ones. Okay, beam characteristics. I'm not talking about characteristics that you see on the image, I'm talking about the beam characteristics. So quality. Okay, the main factor for quality is KVP. Okay, quality just refers to the penetrating power, the energy of the X-ray beam. So the higher the KVP, the more penetrating it is, right? Okay, filtration. Filtration is also part of quality. What does filtration do?
Gets unwanted X-rays.
Good. It gets rid of the unwanted X-rays, which are which ones? No, filters, scatter happens when it hits something. Good. It gets rid of the low energy, the long wavelength photons. Why do you want to get rid of them?
They don't help the image.
They what?
They don't help the image.
They don't help the image, and they're bad for the patient's skin dose. They can't go anywhere. They don't have enough penetrating power, so it adds to patient's skin dose. So that's why they have filtration. Okay, so the more filtration, the more the quality of the beam, because you're getting rid of those non-useful photons. Okay, quantity. Quantity of the beam just refers to the number, put this word down as well, intensity of the beam. The number of photons or intensity of the beam. What's the main factor for quantity? Mass. Good. Main factor for quantity is mass. The higher the mass, the more photons produce. Okay. Quantity is also influenced by KVP. The higher the KVP, the more the quantity. It's also influenced by the distance. So if I move the tube from 40 inches to 72 inches, what would happen to the quantity? A lot less. They don't get there, okay? So if you increase the distance, the quantity decreases. And last thing that affects the quantity of the beam is filtration. Kind of just talked about that. So the more filtration, the less the quantity. You're taking away some photons. Okay, primary versus remnant beam is the next thing, number 3. The primary beam is considered the useful beam. That's what comes out of the tube and hits the patient. remnant beam is known as the exit beam. So just think of, that's what remains as it exits the patient. All right, the remnant beam is made out of transmitted, which means they went all the way through. And scatter.
You said it again?
The remnant beam is made out of transmitted. Those are the ones that went all the way through the patient, and scatter. Those are the ones that bounced off of something. Okay, inverse square law is the next thing on your outline. What is the inverse square law? If you were to describe it to me without telling me the formula, which I wrote there. The intensity of the beam. Something. Close. The intensity of the beam is inversely related to the distance squared.
Can you say that one more time?
The intensity of the beam is inversely related to the distance squared. Okay, so this is the formula for it. So intensity 1 over intensity 2, inversely related, equals distance 2 over distance 1 squared. Am I going to give you numbers to do? No, but you might have it on your registry, so it's not something that you can forget. I will ask you though, so if you double the distance, what would happen to the intensity? Cut it down by what? 4 times less. Good. So doubling the distance, 2 squared is 4, right? So it would be 4 times less. You can also say it's 1/4 as intense. It could also be written that way, right? Because doubling the distance is 2, invert 2, and it's 1 over 2. Square that. 1/4 as intense. And yes, I've seen registry questions just like those two. It could go the other way. If you half the distance, it's just the opposite. They might not give you numbers on the registry. They might just say something like that. Okay, properties. The next thing is properties of X-rays. I'm not gonna, you don't have to do the Rankine rays. I know those. Okay, so the next thing that comes to it in the little outline are the photon interactions. Okay, we're gonna talk about them here. Don't get them mixed up with these electron interactions in the tube. These are photons that come out of the tube and hit the person, hit the patient, or hit an object, or hit whatever. Okay, so the first one I'm going to talk about is something called Compton. A Compton interaction is also known as scatter or fog. It's usually, I'm not going to say always, but it's usually with a high energy X-ray photon.
You say usually with a high energy?
X-ray photon, usually, just so you can get a reference in your head. Some books say over 70 kbp is when you get the Compton stuff. Okay, so it's a high energy X-ray photon. It goes to some cell in your body, whether it's oxygen or whatever, and it interacts with the outer shell electron of that matter, whatever it's hitting. Okay. It just gets deviated in another direction, that X-ray photon. So it becomes a low energy scattered photon. Okay, it does eject that outer shell electron. They call that ejected electron a recoil or Compton electron. Okay, so if you see a picture on your registry, usually you'll see three things happening with Compton. Original X-ray photon, scattered photon, recoil, or Compton electron. That doesn't have enough energy to do anything, okay? The scattered photon, that does a lot of damage. Okay, so Compton interactions are what gives us, the worker, the most dose, because we're standing there, and we get the scatter. Okay, so Compton is responsible for most of the worker's dose. Compton gives you the grays on your image. Okay, next one is photoelectric absorption. It's good that they put the word absorption in so you remember that that's what happens with the photoelectric interaction. So a lower energy X-ray photon, some books say it's usually between 30 and 70 keV or whatever you set. Okay, so a low energy X-ray photon goes into a cell, an atom, and it knocks out an inner shell electron. It gets totally absorbed, that X-ray photon. The ejected inner shell electron, they call it a photoelectron. Photoelectric is responsible for the patient's dose. That's what gives the patient the most dose, because it's absorbed. Okay, photoelectric interactions usually occur with something with a high atomic number in the body. What would that be?
Bone.
Good, bone. Isn't bone white on your image?
Mhm.
Yeah, because that X-ray photon is totally absorbed in bone. So photoelectric gives us our high contrast, black and white. So if you see a little picture of photoelectric, really only two things happen. That X-ray photon comes in, totally absorbed in an inner shell, and you get an ejected inner shell electron. Here you see three things that happen. Okay, coherent. This is the one that doesn't really do anything. This is the one usually they say like a 10 keV X-ray photon. So it doesn't do anything, it just kind of goes by that atom and excites it a little bit and just goes off. So you don't get any ionizations with coherent. Nothing gets flicked away. questions about photon interactions? Okay. All right, so we're gonna move on, and in your outline it's D, attenuation by various tissues. So we'll go to number 2 under D, tissue types in the body. So I'm gonna go from the highest absorber to the lowest, and I'm sure you guys had this. So the highest absorber, what's the highest absorber in your body?
Bone again?
What's a little bit higher than bone?
Teeth.
Good, teeth, heard someone say it. So the highest absorber in the body, hey,
How are you?
how are you? I love your hair.
Thank you.
You going to the meeting?
Oh, yeah. I just had to get some stuff from the office.
Okay,
See you.
good to see you. All right, so teeth is the number one absorber. And then bone. What's next, remember? Fluid. Muscle is next. Fat is next. And the lowest absorber is air. Isn't air black on an image? So it doesn't absorb. If you guys want a mnemonic, I can tell you a mnemonic. Some people like them, some people don't.
Organs don't fit in there?
There's one bad word in there. Not what you're thinking. When I was in school, there were a lot of bad words in our mnemonic. This isn't, anyway. So the mnemonic to remember this is too bad for my fat ass. One of the students made that up about 8 years ago, and it's kind of stuck. Okay, radiation protection is the next section. This is talking about minimizing patient exposure, basically. So ALARA, all that means is you should use as high a kVp as you possibly can to lower your mass. Okay, shielding is the next thing. You should always shield your patient. As far as types of shielding, you guys would be able to pick that up, but I just want to make sure you know what a shadow shield is. What is a shadow shield?
What is not on the,
It never touches the patient, it just makes a shadow, okay? All right, and you should always collimate. All right, then we get to filtration. We kind of talked about this a little bit earlier. That's why a lot of this outline is redundant. Okay, NCRP recommendations for filtration. I do want you to know this, it's a number. Any tubes operating above 70 kVp must have at least 2.5 millimeters of aluminum equivalent for filtration.
you said any two with 70 kVp?
That operate above 70 kVp, which is pretty much any tube at all. They pretty much all operate above 70 kVp. Must have at least 2.5 millimeters of aluminum equivalent for the filtration. Okay, types of filtration. Okay, there's two types of filtration. First one is known as inherent filtration. That just means it's already there. I don't like to say it's built in by the manufacturer, because actually added is built in by the manufacturer. So inherent filtration is just already there. It's part of the tube itself. So give me some examples of inherent filtration. Good, the glass envelope. What? Good, the oil bath that surrounds it. tube housing. So what's added filtration? No. Nope. That's shielding.
The code.
Some books say collimators are part of inherent filtration. Added filtration is the actual aluminum itself. You don't need to know the numbers, but that's usually 2.0 millimeters of aluminum. So my main question is, which is a lot of the registry stuff, where is the added filtration? If you were to describe to me where the added filtration is, where would you say it was?
Did you slide it into
Between the, and the patient,
So here's the whole mechanism. This is actually, the tube is actually up here, right? And then there's a little window and the X-ray photons come down. That's your collimator, right? Where's the added filtration?
On the outside of it.
Nope. Okay, the added filtration is between the tube and the collimator. Don't forget that. That's registry stuff. Okay, you guys might have played with filtration and we have a chunk of aluminum that we just play around with and we stick it on, it just slides onto the collimator.
Yeah,
That's not what added filtration is. Added filtration is, that's why I say it's really part of the tube, and I hate how they say it's not built by the manufacturer. It really is. So anyway, all right. Okay, next thing is HVL on your outline. What is HVL? Good, half value layer. So basically HVL is the thickness of the material. We're talking about filtration. The thickness of the filtration that will decrease the intensity of the beam to half the original. Half value layer. Decrease the intensity of the beam to half the original. Okay, so if I wanted to decrease the intensity of the beam to, pick something easy, 10% of the original, how many half value layers do I need?
Less than.
So your first half value layer, what will it go to? Half. 50%. Okay, so first half value layer, you decrease it to 50%. Second half value layer, you decrease it to what? 25. Third half value layer, 12.5 or something. 4. You need to go 4 half value layers to decrease it to 10%. Let me do an easier number. Let's say that you want to decrease the intensity to 30% of the original. How many half value layers do you need? Good. First half value layer would be 50, second would be 25. 2. You get it? Okay. They might not give you numbers to put into this thing. They might just say that. Or they might say, let me think of another easy number. The original intensity is 90 milligrays. It would never be that much, but let's just, 90 milligrays. to get to 40 milligrays, how many half-value layers would you need? First half-value layer would get it to what?
What did we start?
We started at 90. So the first half-value layer would get it to what? 45. 2. You need 2 half-value layers to get it to 40 milligrays. Do y'all get that? Okay, good. Right, patient considerations, pediatrics. If I skip something, it's because I'm not going to ask you it. For pediatrics, you should always remember, don't use a grid on a PD. Why not? Yeah, it's a lot more dose, because grids, you have to increase your mass. So don't use a grid for PDs. Okay, for fluoro, as far as the patient dose is concerned, the best fluoro machines are the pulsed digital ones. You guys seen them out there? The other groups said they've never seen the pulse fluoro. You've never seen? I thought the VA had one.
Yeah, I never heard of all of that.
Did they call it digital fluoro? Anyway, you can almost kind of see it doing like that. Anyway, so that's the best one as far as patient dose is concerned. It's a decrease in patient dose. When they fluoro, what's the MA that's being used? Good, good. MA in fluoro is between 1 to 5. That's it. MA, when you shoot a conventional x-ray, when you shoot a regular x-ray, it's in the hundreds. Most machines go to like 1,000. So why is there so much dose when you fluoro? Good, because of the time you're standing on that fluoro switch. All right. Okay, here's a couple more numbers that you need to memorize for registry purposes in this thing. The maximum intensity of the beam in fluoro at tabletop should not exceed 100 milligrays per minute. Okay, you can also say that as 21 milligrays per minute of MA used. Because remember, MA can be from what to what? In fluoro. 1 to 5. So 5 times 21 is approximately 100. So that's another way to say it. Okay. If the fluoro has a high intensity control, it can go up to 200 milligrays per minute. Okay, 100 milligrays per minute or 21 milligrays per minute of MA used, or the high intensity booster fluoros, it can go up to 200 milligrays per minute. Okay, fluoro timer. How long is the fluoro timer? Good, 5 minutes. What happens when it gets to 5 minutes? It beeps. Does it turn the machine off? No. It just beeps. I'm going to talk about the automatic brightness control some other time. I think it's in the spring, can't remember. Okay, as far as the receptor positioning in fluoro, these are with the machines that you can move. You guys know what the image intensifier is, right? In fluoro. It's that big white, it looks like a big globe. You have the tube and then you have the image intensifier. Okay, so one thing you should remember as far as patient dose is concerned, always put the image intensifier as close as you can to the patient. It decreases their dose because you're kind of like decreasing the SID by doing that. Okay, magnification mode, I'm gonna go over some other time in the spring. Okay, source to skin distance. Okay, for mobile units, there's more numbers you need to know. For mobile units, the minimum is 12 inches from source to skin.
What was that here?
12 inches for mobile units. You can't get any closer than that. For stationary units, you can't get any closer than 15 inches source to skin distance. They're a little bit higher intensity.
So 15 inches.
15 inches for stationary units. Okay, personal protective. You guys want to take a break? No, I'm almost done, promise. You're all getting tired. Personal protection, personnel protection. Primary radiation, we already talked about that. That's the useful beam. We should never be exposed to the primary beam as personnel. Secondary radiation, there's two types of secondary. First is scatter, which we already talked about. To protect yourself, if you're doing fluoro, how should you stand as far as the table is concerned to decrease your dose? Remember? You should stand at a right angle. Yeah, you should stand at a right angle to the patient or the table, or 90 degrees. Okay, the other type of secondary radiation is leakage. That comes from the X-ray tube other than the window itself. We get some leakage. So here's another number you need to know. Leakage radiation cannot exceed 1 milligray per hour at a distance of 1 meter. Okay, if you stand back 1 meter from the patient, the beam is 0.1% of primary. By just standing back 1 meter, it is 0.1% of the primary. Or it's the same way of saying it's 1,000 times less by just standing back 1 meter. Okay, personal protection as far as lead aprons are concerned. The minimum requirement for lead aprons according to NCRP and CFR fight about what they believe in. So NCRP says lead aprons must have at least 0.5 millimeters of lead equivalent. 0.5 millimeters. CFR people say 0.25 is good enough. 0.25.
Who said that?
CFR. Don't ask me what it stands for. I can't remember. Some nuclear regulatory place. I don't know what it stands for. Okay, but if you have a question on your registry, it says that it's a dedicated fluoro apron. It's always 0.5. A dedicated fluoro apron is always 0.5 millimeters of aluminum. Okay, everything else, the gloves, thyroid collar, the slot, there's on the table, the bucky slot cover, sometimes there's a little cover that you can pull down. Those are all 0.25 of lead equivalent. Okay, primary and secondary barriers. What's a primary barrier? What has to be a primary barrier in an X-ray room?
What has to?
When you build an X-ray room, what has to be primary?
The wall.
Good, the wall. Up to how high? Good. The wall up to 7 feet. Usually no one's taller than 7 feet. What else has to be a primary barrier? Good, the floor. And the door. Those have to be primary barriers. They are 1/16 of an inch lead equivalent. 1/16 PB lead. Okay, secondary barriers, they protect against secondary radiation. So any wall above 7 feet. The ceiling, you usually can never aim the X-ray tube at the ceiling. The control booth is a secondary barrier. And that has to be at least 1/32 of lead. Last thing. Okay, there's some more stuff on fluoro. It's just a repeat of what I just went over about exposure rates. The exposure cord. Exposure cord on mobile units, what's the rule for the exposure cord? Good, it has to be at least 6 feet. So you can stand far, far away. What's the rule for the exposure switch in an X-ray room?
Behind the barrier.
Good, you can't be able to walk outside of the control panel. That's why like our digital room, we had to zip tie it. Cause you can, it was long where you can walk around.
Where people around there?
Huh?
I said where people actually use it.
People X-ray
Like,
themselves.
You need to walk out. Really?
Yeah, hate to admit it, we used to do it all the time. Don't tell me, but I told you that. All right, exposure switch for fluoro. What's the exposure switch called? Good, a dead man switch. Y'all knew that one. All right, that's it. Questions? It's not that bad, really.
A lot of it is review.
Yep. Because I didn't know it, but Terry said she did a lot of this stuff in the spring as well. I thought this was all fall stuff, but she said, no, I did all that stuff. So,
Yeah, she was kind of reviewing for,
what the dean did.
Yeah.
So I don't manifest it.
Nope. Okay. All right, so y'all have your schedule for science comps, because that's the next time I'm gonna see you.
ARRT.
Yeah, you said mine was on the Zoom. You said July 2nd.
Where do we put it?
Let me put it on my calendar.